What's up, hover nerds? Welcome to this week's Tech Talk. Thanks to Ross for putting these on. He's been doing a great job doing all the recordings. So this week I want to talk about basically lightweight transmissions, fan frames, drive shafts, the glue that holds your craft together, basically. All the little bits that you forget about once you've got your shiny new hull and your engine, and then you realize you're only halfway there because you've got to do all the complicated bits. So I've been building racers for since 2004. On screen you got my current racer. I think that's the 7th craft I built, and I just wanted to go through a few of the fancy fan frames and drive shafts I've been building over the last 10 years, basically to try and build faster, lighter hovercraft. That's been the goal of why I've been putting effort into it, but also it's relevant for cruisers, as Keith was explaining in his quiet hovercraft talk. The more aerodynamic your frame, the less noise you're going to have, better cruiser. So here's an image of the first carbon fiber fan frame I built on a Formula 3 craft. So this has got a TZR 250 engine, 50 horsepower, and on the image on the left, you can see the fan frame, duct, and flow straightener unit. It's all one piece of carbon fiber. That weighed about 10 kilos, and it was pretty damn strong. And it was really clean as well. So it produced a load of thrust, and inspired by Owen Ellis, who did the talk previously on electric hovercraft. It's got the belt drive coming from behind the fan. So that means there's nothing in front of the fan almost, apart from the radiator and the engine, but about 200 mil away from the fan, it's completely clear, which is really good for the fan and is good for producing thrust, basically. About 5 years later, I moved on to Formula 2. This is about 2015 on my Pintail. This also had a carbon fiber fan frame, but it was slightly more modular than the previous one. So the flow strainers at the back are a single piece carbon fiber piece, kind of integral to the hull, and they basically hold the fan in the middle and resist the thrust force from the fan. But up front is a thin steel frame, which is the thing that prevents the two pulleys coming together and overcomes the belt force, the belt tension, which I'll go to talk about in a minute. But the belt tension I've found to be one of the biggest loads that these frames had to deal with. This craft was also pretty quick. I won a few races, had some good racing in it. But there's always the worry when you're doing a frame like this. If you flip the craft and you damage your flow straighteners, you're out for the weekend. Or if it's a world championship, you're out for the whole week, basically. So that's the reason why recently, on my most recent craft, I've moved away from that. And I've gone to a slightly more modular frame. So here's a video of the first start of my Eurocraft, which has got mid-engined. It's got a long drive shaft up the front there to power the lift fan coming off the motorbike engine sprocket, and at the back, coming off the clutch output, there's a 0.5 meter drive shaft going into the thrust fan there. That's what I'm working with at the moment, and I'll show a few more details of that in this presentation. Here's a CAD kind of view of this craft, and if we zoom in on that CAD view onto just the transmission, just the thrust transmission, I'll just describe a bit about the major forces that I've used in the design of this setup, at least. We got a 300 Newton meter torque coming out of the engine, going along that drive shaft. And that's a heavily factored load. because if you work out the average, I've designed this thing for 200 horsepower if I wanted to upgrade the engine at any point. But if you work out 200 horsepower divided by 8,000 RPM, the torque that you actually get is more like 90 Newton meters. But the reason why I'm using 300 for design is basically to account for the fact that you get torque spikes when each piston blows, and that basically is the sort of shock loads that we would typically use in engineering when you're designing drivetrain stuff. So when you put the torque into the frame, then it goes and produces the belt force, creates tension in the belt, and tries to pull the two pulleys close together. And I'll explain in a bit how I work that out. It's really simple. But yeah, you can see that the belt force is near to a ton on this craft. And then we've got the thrust force, which is what the whole reason for this is to create thrust. And here I've got about 3 kilonewtons of thrust. That's assumed. In reality, I've only measured about 450 pounds of thrust coming out of this craft, but room for improvement. I've got plenty of room for growth. If I put my fancy fan on there, or if I put a turbo on the engine, then it should be fine. And then the smaller force is fan inertia. That's basically the weight of the fan and the frame when you go over a bump in the craft and it tries to rip the frame out of its mountings. And you can see that's quite small because it's quite a light fan frame. There's a load of other forces going on which aren't really taken into account in the calcs. Detail things like fatigue, vibration. It's really tricky to go into the details on these, and I don't really want to be doing that in my spare time. So to account for them, that's why all these quite large factors are added on there, like the 3 times for the torque, and various of like on the thrust as well. Yeah, so I'll just move on and just explain how the biggest force that acts on the fan frame is calculated. Is really easy. You just take the torque, you divide that by the radius of your little pulley, because that's what a torque is. It's just a force at a certain distance from the axis, and do put a little factor in there. There's a 1.25 factor in there for pretension. So when you set up your fan frame, you have a bit of pretension in your belt, and that's what that 1.25 factor is in there. That's a pretty generous factor. It probably isn't like that in real life, but if I accidentally wound that belt up super tight, then I'm covered. So on the drive shaft itself, here's a little quick calc to work out what shaft to use. So on my, I'm using 2-inch aluminium tube with bonded end fittings. And if you run these calcs, you'll find that you don't need much of a shaft at all. It's pretty simple calc. If you just type in your outside diameter, your inner diameter, you work out your polar moment of inertia, and then you get your shear stress out if you use this equation. In this case, this aluminium can withstand a shear stress of about 110 megapascals, so it's fine running at 50 megapascals. It's more a thing of finding a tube that will fit and making sure it works nicely with the sort of the end couplings that you can buy. The more tricky thing about drive shafts is the end fittings. So here's a little image of the machined end fittings that I bond into these tubes. I sized the area on this end fitting so that when you break it down and you do the similar calc to the when you were working out the belt tension, you can do a similar calc if you follow the steps on the following slide to work out what the stress is in your bond area. In here, we're probably pretty low. If you work out the average, it's something like 5 or 10 megapascals. And the glue supposedly in shear can take around 30. But the point with when you're doing bonded end fittings, you probably want to test what you're going to do. And in this case, I did build a test piece using exactly the same glue, exactly the same surface prep, and then post-curing the end fittings the same way that I would any of the drive shafts that are on the craft. And I basically tested it because there's so many variations with using epoxy, etc. Also, with bonding joints, if you look at the image on the slide there, you can see that you get red colours towards the end of the bond. What you're seeing there is a section through where the bond actually is in the tube, and always at the ends you get a really stress concentration. So that's something, if you go into the detail, that you need to look at. One other thing about drive shafts, if you've got particularly long drive shaft, like I have on the lift fan on my F2, you can get close to the critical speed. If you operate at the critical speed, then that means the shaft is resonating, and especially when it's between your legs, it's not a good time. So yeah, you want to avoid that, and a way to do that is to basically check it in using this simple calc here. Get in touch if you want me to show you the way to get through this, but it's pretty, I found this calc to be pretty accurate. Even when I've used the kind of professional engineering programs, found that in the application that we're using them, at least, this quite simple application of a shaft, 2 couplings at the end, well, I haven't had any problems on the F2, and back in the day I didn't have any problems on the F3, so it must work. Just move on now to the fan frame itself. On the screen I've got a few images of the development working through from the first concept on the left there, and then on the right got to the final design. Yeah, so here's the fan frame itself. What we've got is a carbon fibre piece in the middle, and we have aluminium bearing blocks up at the top and bottom. So yeah, I went to the effort of making this thing mainly because the frontal area is extremely low, and the only thing in the airstream is the belt, which is going to be fully covered at some point when I get a full shield over it and get a nice nose cone on the front. And the other thing to note about this frame and some of the others that I've been doing over the years is that it supports the weight of it supports the belt equally at the front and the rear, and that means you've got no troubles with belt tracking like you can typically get in a more common fan frame setup. So yeah, here's a few more details of the design of this frame. On the left is a picture of the FE model. I was basically checking to see it wouldn't deflect too much under the loads that we worked out earlier, and also checking where the stress spots are to make sure that I basically put enough carbon fibre in that area. From this model, found that I had to put a load of extra layers down at the bottom where the bearings bolt on at the corner, which is where you'd normally find the stress razors. Yeah, and on the right picture there's a picture of the tooling that was used to make this thing. I've printed the 2-part mold from plastic. I've wrapped it in vinyl, and then I vacuumed the mold over it, which worked quite nicely. So, and then the final thing on fan frames. I've got here a calc that you can do on the standard frame layout where you've got the overhung pulley. That's where you've got the pulley sitting behind the upright, and that in itself, with the tension of the belt hung over the back of the upright causes the upright to try and bend. And obviously that in the worst case, you can have your belt fall off the back, which we see a fair amount in the field. And if you run down this simple calc on the screen here, you can check how much upright bending you get, depending on your torque that you're putting into the frame. If you guys got any other particular questions you want to ask about in the Q&A after this session, I've got an extensive library of Excel calcs for all sorts of frames, so please send through some questions and I'll try and help you out with that. But otherwise, thanks for listening. That's pretty much all I had to talk about fan frames. I do have one little bit in response to Richie's excellent talk on variable pitch fans. I've got here a lift polar from the multiwing 5Z fan. So what I did was I took the fan blades, I cut them up into little sections, and I basically took these sections into the computer and then program spit out what's called a polar. This basically tells you how much lift or drag you get at all different angles of attack. And you can feed this into fan design programs to work out how your fan's going to work. So let me know if this will be of use to you guys, and I'd be happy to share it. Anyway, thanks for listening, guys, and that's all from me.